nicely said. Actually, I'm a nice guy. Okay, so yeah, I'm going to do this talk in English. If you have any questions in Polish, Piotr will translate that. So don't hesitate to ask questions. In general, I have a couple of slides prepared here, but I'm way more interested in interactive discussion rather than just me talking to you and telling you interesting stories. I would rather prefer if we could get a discussion here going with you guys asking questions and I answering, and maybe even me asking questions to you and you answering. So yeah, if you have a question to something that we cover, immediately ask. And if you have anything that you want me particularly to talk about, I'm totally happy to do that. Just interrupt me if you think it's the appropriate time. The slides I have are not so much technical. I mean, there's a couple of slides in the back that aren't technical. I want to talk more about the politics and about the way and the history of systemd, rather than the actual technical stuff that is in there. I mean, I usually talk about the technical stuff, but I thought in this case it might be interesting, like the stuff that you can't read on the internet, that you can't already watch on some website, which is just about the politics. So the slides I prepared, the first bit is about systemd, the history and the politics. Then there's a short section about what we can learn from that. And then there's another section about pulse audio and the history and how that was. And finally, it's a little bit about the journal. And then afterwards, I have a couple of slides about the technical stuff. But I don't expect that we actually cover all of that. It's just that I want to have all the slides ready in case somebody of you asks. If I understand correctly, afterwards we'll have a little bit of a panel discussion anyway. So if you have some really exciting questions, I'm totally interested in those. But yeah, if they are more appropriate for the panel discussion, leave them for the panel discussion. Anyway, I guess that's all I have to say in advance. I know that I speak quite fast. I'm sorry for that. It's hard to control. If I speak too fast,
I'm gonna wait there.
Then just say something, and I try to speak slower. So it's actually very hard. Anyway, so the title of today is Hacking the Core OS, Pushing Big Changes. Yeah, the background of that is, of course, that we push systemd into Fedora and OpenSUSE and a couple of other distributions. And that is a relatively big change. It's probably the biggest change that has happened in Linux in the last, I don't know, 10 years or something. Because most of the basic infrastructure of the core OS used to be pretty much the same. And actually, the basic exists almost when it was created. So, yeah. Anyway, I think this slide is not that interesting because I was already confused.
Go on.
So,
get back. Explain who you are.
Okay, so I'm a software engineer at Red Hat. So I think there was a lot of talk about Red Hat earlier. I didn't understand a word. I hope it was all good that was said about Red Hat. But yeah, so I'm one of those engineers. I developed a largely pulse audio systemd and a couple of other projects. I've been doing this for quite a while. So yeah, if you want to reach me, that's how you can reach me. And that's all I have to say. Okay.
Can you get back to the IRC part? How can you be reaching IRC? Which network is this?
As most developers of Linux, I guess, or at least, yeah, I'm hanging around on Freenode all the time, and you can find me on the systemd channel and a couple of other channels too, and I also hang out on GitMap and Fedora channels and whatnot. It's not that much fun, as long as you know the IRC nickname. That's the only thing that keeps me from getting chatted to all the time. People don't know. Anyway, so yeah, the first part of it is systemd. Why and how? Yeah, let's talk a little bit about systemd and what the history is, the reason is, and what we're comparing it to, like what was there before systemd existed. The benchmark that we needed to match with systemd was System 5 init. System 5 init is a re-implementation of the classic System 5 init system, which is basically from the late 70s, early 80s. This free implementation is very, very old. It's like from the early 90s and hadn't changed at all since then. System 5 init is a very, very simple init system. It is in a couple of ways. It feels a little bit archaic in the way, for example, it knows exactly 6 run levels. 4 of those are useful. The other ones have special meanings. And those run levels carry numbers. Nowadays, computing is not that. I mean, nowadays you try to be more descriptive if you invent concepts like run levels or something like that. So it is a software that was very simple, very linear, very not event-based, very yeah, very, very simple, very trivial concepts. It was already better where it existed before, and was widely used across all the distributions. Then we had I and Kai and a couple of other people. Kai Zivers is the other guy who works on System B. Like, okay, there are two more people who work on System B, plus a lot of people who send patches. But Kai Zivers and I...
Do not lower your voice.
Do not lower my voice.
No, no. Do not make it speak louder.
Speak up. Speak up.
Okay, I should be louder then. Okay, so the benchmark back then was System 5 Init, and we looked at that and always got the feeling, this is we can do it better. Other distributions, other operating systems like macOS, like Windows even, had better service managers than we had on Linux. Because in Linux, services were...
Blasphemy! That's blasphemy!
on Linux and Unix, services were mostly unmanaged. If they were started, they were on their own. Nobody would restart them. Nobody would make sure that if they fail, somebody notices that. They were completely unmanaged. So we thought, hey, this is not how we do these things. Not in the 21st century. And so we started working on a project. We called it. It was very early actually. It was in 2008. We called it BabyKit. It was that time where all those daemons that were done for the Linux-based system were called something kit, and the BabyKit is kind of funny. So we started dabbling with that and get a couple of ideas how these things should work. Yeah, well, after doing that, a project emerged called AppStart. AppStart was an init system. It was written from scratch and had completely new ideas. The guy who wrote AppStart, Scott Remnant, he looked at System 500 and came to the same conclusions as we did. Yeah, we can do it better. It needs to be services nowadays need to be managed, and yeah. So he wrote AppStart, and we thought, slow down. So he wrote AppStart, and we thought, wow, somebody's doing something about it, and we actually liked the code of AppStart. So obviously, AppStart is the future, and that's why we dropped BabyKit at that time. But yeah, as the history goes on, eventually we noticed that AppStart is not going to be what we wanted it to be. Like, this had a couple of fundamental issues we saw with AppStart. One of them, the most core about it, was basically that we saw the entire design, basic design of it, was flawed. The reason for that is AppStart did something much better than System 5 did. The AppStart developers realized that boot nowadays is entirely event-based. So if you look at the boot process of a modern Linux system, or any system actually, any computer system, you will realize that what is done there is basically, it reacts to events, and then does a little bit, and reacts to the next event, and does a little bit, waiting for the next event to do a little more. These events could be, yeah, wait until the hard disk so-and-so appears. Run fsck, wait until fsck finishes. Then mount something, and so on and so on. And all these events together, they can happen completely in parallel. For example, if you have 10 disks, you would get 10 events. And sometimes you need even more complex logic. It's not just sufficient like to fast check and mount the block device, the hard disk that shows up. But sometimes you need to assemble RAID and assemble LVM and these kind of things. So you end up with a boot process where you have to wait for external events, for internal events, and always do something. That's what he realized. And that is what already much better than System 5 Init. Because in System 5 Init, there were no events. It was just a simple linear execution of scripts. And in this classic design, the simple linear execution of scripts meant that since nobody was watching for events, you had to start everything and then wait until everything appeared. And then after you saw that, oh my god, now everything appeared, you went on to the next thing and executed that. So basically what AppStart did there is get things right. It worked closer on how the kernel actually worked internally. And yeah, so it's a nice design in a way because it is exceptionally simple. What AppStart basically did is on all these events, it basically gave names to events. Like hardware plugged in, got a name. Service started, got a name. Service stopped, got a name. Service failed, got a name. And then you could attach actions to that. It's a very, very simple design. AppStart is a very, very tight code base to do that. We actually like the code base. I actually like the code base of AppStart a lot. But we also figured out it is not what we actually want for an init system. The reason for that is the following. If you look at the boot process of a modern machine, you'll figure out you want to reach a certain state. You want to reach that state where Apache is running, where MySQL is running, where GDM is running, and all these a couple of other things. And that means you need to start exactly that, and everything that requires. That is called basically build up a dependency tree through that. You know what you want to reach, you follow all the dependencies, and then you know everything you need to start, and then you just care about the order and execute it. That's how a boot process should work. Upstarting, instead, works differently. They have these events. So these events are triggered, and then they look, okay, what should we now start? You can map one to the other, but the big distinction between that is, in Upstart, it's the job of the administrator or developer to actually encode these dependencies to the events. So that whenever an event happens, the administrator has said, yeah, if this event happened and this event happened before, then do this. While the dependency-based stuff just said, yeah, this is the goal, by the way, you need all of this, and then the computer does all the automation. So the big design flaw that we saw in Upstart was the design was super simple and hence kind of sexy. However, it did not do where the actual problem was, because it didn't solve the dependency problem. It didn't include the graph theory that you need to figure out exactly what you need to boot up and in which order. So this is a very fundamental flaw. It's a basic fundamental flaw of the design of Upstart. There were a couple of other things that made us a little bit unhappy about Upstart. For example, how do you keep track of the daemon and all processes it starts on Linux? Previously, this was completely impossible. So if Apache started and spawned off CGI scripts like a dime a dozen, then there was no way to figure out which CGI script was actually belonging to Apache. I mean, there was an official way, which basically meant that CGI scripts are just child processes of Apache, but it's really easy for a process to escape that, and processes all the time did. So you have no idea about, if Apache goes down, you probably want to stop all the CGI scripts that spawn as well. But how do you figure that out? So in the Linux kernel, a certain technology was invented called control groups. These have been, like the C originally was supposed to usually control groups are just called C groups. The C of that kind of suggests the original usage, which is containers basically. That's why they were created. But we saw this is actually a really useful tool. Control groups basically allow you to put labels on groups of processes and order these groups in a hierarchical fashion. And we noticed that, oh my god, this is exactly what we need. Because then we can label at the Apache service all the processes that Apache started, the main process and the CGI script. We can label that together with one label and even do that hierarchically. And then after we labeled it, we can implement on top of that, like kill all the processes of Apache. And that's really easy. We just have to kill all the processes that have the label of Apache.
What about the order of killing the processes within the group?
What systemd does is basically first kills the main process, and if that doesn't react, kills everything else in no particular order. It's not defined. We saw that this functionality was available. It just somebody needed to make use of that. We tried to convince Scott about these things. There were a couple of other things like that, but it was mostly not interested. And so we sat down, and this went on for a year or something, and eventually we came to the conclusion. Yeah, the project is flawed, the design is flawed, and we're not getting anywhere close to what we actually think how these things should work. And then we saw, it's always a big decision to start from scratch when there's already a project that's actually thriving. The Buster was kind of successful like that. And however, we saw, okay, if the fundamental design, the really basic thing, is flawed, then this is reason to start your own thing. So that's basically the benchmark. System 5 really archaic, barely maintained at that point. Nowadays it has a container again, but it's really, really slowly moving. And Upstart, which was, it was also relatively slowly moving, faster than System 5 but it had this huge thing that the basic design was flawed in our eyes. So yeah, for a while we thought that Upstart was the future. We came to the conclusion, probably not so much. Basically already talked about this. Upstart implements an event-based boot, a strictly event-based boot. You just say, execute this when that happens. Systemd implements a dependency-based boot. It basically says, yeah, this is the goal where we want to boot to, or what the user wants to start. And systemd's job is to calculate what is necessary, to wait for what, to start what, and so on. So yeah, this is the basic design distinction here. So yeah, when we then decided to dabble around with writing an system, we took a little bit like from the baby kit stuff that we did before. We figured out that by the name baby kit, we would probably never have the chance to get them into the big distributions and supported by companies because it was just a funny name. So we basically integrated the code, gave it a new name, we just called it systemd, because we thought, yeah, it's the daemon that's supposed to pull together the entire system, and it's a Unix daemon, so it needs the suffix d, so we called it systemd. While doing this, we thought, yeah, Linux has one big problem, that is balkanization. Balkanization. Balkanization, basically fragmentation.
Okay.
Like, so basically, there are all these little fiefdoms, all these distributions, who all basically do the same thing, but vary in configuration files, even if it's the tiniest configuration files, the most irrelevant ones are different among the distributions. For example, I don't know, if the place where you configure the console font, every distribution, SUSE, Red Hat, Debian, had its own configuration file for that. And it's a completely trivial configuration file. It just contains basically one setting. This is the name of the font to activate. So we saw with systemd, we can do this better. We can use systemd as a vehicle to push for standardization of these really basic, really boring configuration files, so that the distributions do not distinguish in that way anymore, and the administrators in the long run will have it easier. Of course, there's a little bit of irony in that. Because if you want to get everybody to standardize on a format, it's usually a very bad idea to push a new standard that is incompatible with everything that was before. So our answer to that was, yeah, where necessary and where it makes sense, we invent some new configuration files as simple as possible and as Unix as possible. When not, we just declare one of the existing formats the standard that we will support the system. The net result of that was that we adopted quite a few configuration files from Debian as something we want to support officially in systemd, and very little from other distributions actually, which is of course interesting given that I'm actually a Red Hat Fedora guy. So yeah, we saw that if we do this properly, then we need to get everything standardized. This also meant a couple of other things. In System 5 init and even in Upstart, there was this huge problem that init scripts were written by the distributions, not by upstream. This had the result that it was a lot of work for the distributions to adopt the different services because they would have always to write those init scripts. And secondly, these init scripts were varying quality because all the distributions, some spent more love to it and some less. And it's also, yeah, it's just a huge waste of time and a huge source of errors. And yeah, we thought we can do something about that and put the emphasis for init scripts, not on the distributor, but in our replacement for the init scripts, put the emphasis on the upstream developer. This, of course, is kind of new because init scripts doesn't work like that. But there's enough examples where this actually worked out. Like, for example, bus services, like for the desktop bus, for eBus. They tended to be always shipped upstream and not added by the distributions. And there are a couple of more examples like that. So we decided, okay, yeah, we can pull it through. So anyway, the basic design ideas that we had with systemd was, yeah, standardization, and also the reduction of duplication. If you look at the classic Unix stack, you'll find there is one way to start things in a tab. There's another way how you can start things in init scripts. Both of those you can start at boot. And then there's another way how you start things based on time. It's called cron. And there's another way how you also time. It's called at. And there's another thing how you can start things in hardware. It's called udet. All of these things do basically the same thing. They have some kind of trigger, and then they execute something. And they all have very, very different. Like some of them allow you to set shell variables. Others allow you to set the umask. Even others allow you to set resource limits. Some allow you not to do anything of that. So when we looked at this class of Unix stack, we noticed, oh my god, this is always the same stuff implemented over and over again, and different again. So this makes no sense, because A, it makes it complicated for the administrator. Sure, if you're a seasoned Unix administrator, you know the difference between cron, apt, system tab, init tab, and in system file init scripts. And you know how these differ and what you can do in the different things. But if you, for a newcomer, it's completely makes no sense at all. It's all four kinds, and they're actually more like, for example, inid and stuff like that, which also has completely different capability. If you take all these together, you notice that, oh my god, this is all different. It all does the same stuff, and all of them suck in a different way. And so we saw this, yeah, so starting services, starting processes actually is a really important thing. Because you want to set properties to make it secure, you want to set properties to make it safe, you want to set properties to adjust it to exactly what you need. And you want to apply resource limits and all these kind of things. And you need this in regardless how you start. So we said, yeah, our emphasis, our focus, the system, will be to reduce this duplication. That way we get a smaller system with more features that is easier to understand. However, it comes at a price, of course. It is very different from what the classic Unix was before. So yeah, anyway, so these were the two big drivers about the design of the system. Of course, if you start such a project, you need to look around. Like,
we can cut it out from the video. Speak freely, we're gonna cut it out. You know what I'm talking about?
Yeah, no, but actually I like both of them.
Okay.
I actually like Upstart as well. I mean, don't get me wrong, I'm not going to shit about those two. They seem like good sources of inspirations. I mean, I can say bad things about a couple of things in there. But anyway, so if you start a project like this, you better do your homework and figure out what are the strengths of the existing solutions. And there are a couple of things that are particularly interesting. Like, it doesn't have many strengths, but it has one strength. It is supported absolutely everywhere. Like all closed source software, all upstream projects kind of support it in one way. If you buy Oracle, it will include init scripts for all the different distributions. So yeah, what do we learn from Testify Linux? We probably need to provide compatibility with that. But from Upstart, what can we learn from that? Not too much. I've said it's a much cleaner design, and pretty code is pretty, and event-based is the way to go. But we knew that anyway, I guess. But the others, the more interesting ones, were SMF and LaunchD. SMF is Solaris.
System management framework.
Exactly. It's basically a system before Solaris. It's much older, and it comes from a different phase, I guess. And from a phase where XML was still absolutely the rage, and everybody loved XML. So the service configuration. By the way. It was based on XML. It is reasonably powerful. It had a dependency system, but it also was a really weird thing because it actually lived side by side with system 5 init. So they didn't actually get rid of system 5 init and replace it with something newer. They just let everything run side by side. SMF has a couple of interesting features. A lot of them is like really enterprise stuff. And it has a couple of weaknesses, like for example, I don't think it's a good idea to write XML for anything that is not actually documented. I think you guys teach Solaris as well. You probably know all the details about SMF. But it's an inspiration because, for example, health it does quite nicely. So we looked over that and then thought, okay, these are a couple of nice features that we should probably provide on Linux as well. And then LaunchD. LaunchD is something developed by Apple. It is a part of Mac OS X. It is actually really good design. It has this feature called socket activation. I'm not going to go into much detail with that, but socket activation is like the biggest thing that they invented in service management in the last 20 years, I would say. It's actually a super trivial idea, and it's not even a really new idea, because it's something that was implemented by inid about 20 years ago. It's an absolutely unique thing. However, they used it in a completely new way that allowed them to get rid of dependencies for the main boot process. Not for the early stuff, not for the late stuff, but for the main processes, they don't need any dependencies at all. It is really, really nice design that way. LaunchD itself was Apple code, I guess, which means usually many of the design ideas are awesome, the implementation not so much. So it was also very BSD specific and didn't make use of anything that we had on Linux, like for example C group stuff. A couple of distributions did actually consider adopting LaunchD in Linux too, but they decided against it because the change was too drastic. Because there was no path how you could run System 5 and LaunchD side by side. You would have to go all the way. So yeah, but it's a really good inspiration. Like the socket activation thing is like, wow, awesome. Why didn't we always do it like that? So yeah, we looked at the others. We tried to analyze what is good about it, what is bad about it, and steal the good ideas and leave the bad ideas out.
Borrow, not steal. Borrow.
Well, yeah, of course.
Steal it, take something away from them. Sure, yeah. Channel T.
Yeah, we got inspired, but.
Are you sure that socket activation is not Apple?
This is not recorded, right? So I didn't
We're
say
gonna cut it out.
was-
Make it easy. We're gonna cut it out.
But
Excuse me? There is also some framework created by Mr. Bernstein.
Daemon tools.
Demon tools. Yeah.
Exactly. So we looked into that as well. Everybody understood the question, right? So I guess I take that as a yes.
Yeah.
Daemon tools is something written by DJ Bernstein, the guy who is known for Qmail and cryptographer and an awesome guy. It is very simple actually. It is a very simple project. I think I can say that everything I looked into detail into it, what it actually can. It's a very weird beast. It doesn't behave like Unix behaves, like it uses directories in a very creative way, the same way as he did with Qmail basically, where he reinvented
the
stuff.
wheel.
Hmm?
Reinvented the wheel.
Yes. We looked at that, and I think what that can do is something we can do anyway. So I think it's a very minimal system. That is of course nice in a way, but I think it's not as big as an inspiration as LaunchD because it doesn't have any like radically new idea that revolutionizes everything. There are of course a couple of other init systems as well, but in general, I think none of them really tried to come up with something radically new. Or was really commercially driven and hence like really useful. I mean, there's unit engine and stuff like that, and they had some crazy ideas. Like it was totally modular, and you could load a shared module for changing directories before you spawn a service. And that is, I mean, I personally always laugh about that because it's like, yeah, you do dynamic loading for one system call which is changed here. Anyway. So yeah, we tried to do our homework. And I think we succeeded so far and got a couple of ideas from what they're doing. By the way, if you have any questions, I can just repeat it, just interrupt me.
How do you measure success?
How do you measure success?
How do you measure it?
So basically,
pissed off.
basically, I think in this regard, we would measure success like the amount of feature requests that people come up with that this is awesome in Solaris, why don't you support it? I mean, it does happen from time to time, where other people have implemented something really cool, and we totally should have that too. But in general, I think that this kind of stuff is really low. It's not coming every day. So.
Okay. Another question is, did you have to deal with the law department or legal department of one of the companies? Like, hey, this is our idea, why did you steal that?
I mean, no. But I probably shouldn't comment on any legal stuff anyway, so that's good.
We're gonna cut it out.
So, yeah.
One more question. You said that you have a success with DBus shipping unit files upstream.
Yeah.
Who is the maintainer of DBus?
So, for a long time, they didn't really have a maintainer. And then I was kind of the maintainer because nobody else was it. And now it's signed with Vidi. And it is actually paid for maintaining DBus, and that's awesome.
So does it have any input on the success of shipping that you are the maintainer? Is it connected that you are the maintainer?
No. It never worked like that. In DBus, you always have to get at least somebody else to sign off changes. So it's not like when I was a maintainer, I couldn't just push it in. It just meant that I was the idiot who had to do the tarballs and upload them and this kind of noise because nobody else wanted to. But regardless, in DBus, you always have, like, if you have a patch that's sure as it may be, you always have to get an okay. I mean, honestly, I think it's kind of over the top, the kind of bureaucracy in that area. Like, if it's a trivial patch, I would just go on and commit it, but that's how DBus works. I didn't make the rules. But, yeah. Anyway, so, design system lead. I'm not going to go too much into technical detail what it all can do. If you're interested in what it all can do, that's actually, we wrote an article in the German magazine CT, and this article was actually, it was already published 3 months ago or something. That article was actually translated to English now, and appeared yesterday on the Age. Like on this English version of Heise.de, which Heise.de is like the most important German technical news site. Anyway, if you want to know all the detail, I can only recommend you to go to that article. I actually happen to have it open here. Let me quickly show that to you. So yeah, find that website. Yeah, it's kind of hard to read, I guess, the URL of that. But that's the article. If you want to know all the technical stuff, what we've done, designed into it. It's a good introduction, I believe. But then again, I wrote it, so I might be biased. Yeah, if you're looking for that URL, it also was posted on LWN. So go to LWN and you find it's currently, I think, the third article on LWN. So yeah, so we wrote systemd. Initially, basically only as an init system, but then we realized that I already kind of touched that with this thing what I said about the console setup, but we figured out that yeah, it's probably not enough writing in pure init system. The boot processes of the different Linuxes are more complex than just the init system. For example, they set up the console, they mount all the file systems, they do a couple of the quota, they configure all the devices, and all these kind of things. And these things were another thing where all the distributions did the same thing, but did it differently. And so we thought, okay, maybe we should just pull that into systemd. Not into the PAD1 process, but just ship C implementations, fast, reliable, clean, unified implementations of these very simple scripts in systemd long. So we kind of redefined systemd a bit in that area. So it's no longer just an init system. It is now a basic building block you build an operating system from. This, of course, many people don't like that idea, because suddenly they believe that this is against the idea of Unix, because in Unix everything is separate, and then you have your huge bazaar and pick the component and put them together. And we, however, said, no, we don't want it like that. We want to have something that is more developed the way, I don't know, FreeBSD is developed. Something like a tightly integrated basic distribution that is common between a basic building kit that is common among the distributions, and which has the best code possible, and is fast because it's written in C, and easy and not easy to fuck up. So yeah, we did this little bit of shift of the definition of what systemd is. Systemd since then has grown a couple of more modules. All these modules do different things. Like, for example, there's an implementation in there that does read ahead. Read ahead is a technology that you need on desktops, you don't need it on servers, that speeds up your boot. Basically, it just looks what was read from disk on the previous boot, and then will, at the next boot, quickly read that into memory, so that when the system then goes on booting, everything's already in memory and the boot is faster. We thought this should be a component of this basic building set of toolset of building distributions, because I mean everybody needs that, and all the distributions, all the implementations that we had that we looked at, were all kind of like all of them sucked in a different way. Like one of them, for example, required a kernel patch. The other one required use of the audit system, which is totally not for this kind of stuff, but for security purposes. And by them using that, they broke the audit system. And there were a couple of more implementations that sucked in a different way. And we said, yeah, we need this. We think we can do it simpler nowadays because we have nice kernel APIs. And it is something that actually needs a little bit of integration with the init system, because it needs to be started very, very early, and needs to sit in the background and do the right thing. So we thought, okay, yeah, let's pull it in. So over time, we grew a couple of components. All these components, okay, not all of them, but most of these components are actually optional. It's like a Linux kernel, basically. On the Linux kernel, you do make menu config or something, you pick exactly what you want. With systemd, it's a configure script. You can just say, I want this part, I want this part, I want this part. So we basically make this offer, like, hey, you can use all these components. They're very well integrated, very well tested. It's the code that Bazaar uses. It's the code that is supported by Red Hat. You don't have to use it, but use it. We think it's great. So yeah, so we did the shift.
What are distributions? other than Fedora and Red Hat are gonna follow the system integrate?
So OpenSUSE already did.
OpenSUSE.
Yeah. So the big commercial server distribution kind of did. The system is available in most other distributions as well.
Okay, one big question. What about Debian?
So it is in Debian, but they have this huge discussion going on. Basically, they have made this mistake, how I would call it. I think they disagree about that. But they basically have this thing that they saw that it would make sense developing not just one distribution, but a couple of them by supporting a different kernel, the FreeBSD kernel, below the system. I think it's a bad idea. It's a toys thing. Nobody uses that except a couple of people who actually develop that stuff. But anyway, they probably completely disagree with what I'm just saying, because I just say, yeah, why do you do that? It's just a huge pain in the ass. It makes everything more complex and nobody uses it for anything real. But anyway, so they decided to do that, and for them, that's important. So with systemd is something that is very closely bound to Linux. We use a ton load of Linux-specific interfaces. Why do we do this? Not to piss off people who work on Debian K3BSD, but simply because it gives us the ability to write smaller code, because we don't need all the compatibility clutches. We don't need the abstraction layers and abstraction layers to support different backends. And many of the stuff that we rely on is not available in any other kernel anyway. Like the C group stuff, attaching labels to processes. It's not available anywhere. But it's kind of essential for building this. It's kind of the core of what we're doing. So you always see these discussions on the internet about, oh my god, they're so evil, they don't support the BSDs. And the thing is, by supporting the BSDs, we would make our code drastically bigger, because we would have to keep all these abstraction layers. And we would make our code slower, because we always have to go through all these layers.
And maskable interrupt?
Yes, you may.
Good.
It would limit us in what we can do, because we couldn't make use of C group then. And yeah, you always have this discussion on the internet, we're so evil. And most of them, they say, yeah, it would be so easy supporting the other operating systems. Most people who claim that have no fucking idea of programming. This thing is like, come on! The thing is like, sure, there are a couple of things you can probably easily implement with different functionality on the BSDs. For example, our main loop uses the Linux ePOL, which is Linux-specific API, which is a very efficient way to do a main loop. FreeBSD has something that is not ePOL, but provides similar functionality called KQ. Now, we could support both of that. They're very similar, so we could write the abstraction layer. We would have to maintain user code, but it would basically work. But there's all the other stuff, all this stuff where it really becomes complex, like C groups. There's no replacement for FreeBSD, and people who claim that, they have no fucking idea what they're talking about. The reason is, like, they always come up then with ideas, oh my god, they got jails. But no, jails are something completely different. You can't use them for this. Anyway, long story short, towards the question, for Debian, there's portability to these other kernels. I would call them toy operating systems, managed along. So they have the problem that they can't adopt systemd, because then they have the problem that they can't use the basic, or they claim they can't adopt systemd, because then they have the problem that they would have to do something about the FreeBSD port, either give it up or port systemd to it. But we already made clear we don't want these patches upstream, because it would turn systemd inside out. It would make something completely different, and it would enlarge what we have to maintain, because it would always have to go through abstraction layers and all these kinds of things. And so we basically say from upstream, no, we're not interested. We don't want to maintain that. We think it's technically unfeasible to do that, and we'll destroy everything. So they basically have this problem with adopting it, because they care about FreeBSD. My personal suggestion about that, but apparently they don't listen to that, is if you choose to support two different kernels, then go for it, and also support two different init systems. Use classic system 5 init with classic init scripts on FreeBSD. Use systemd in Linux, and they should both. We actually made sure very carefully that you can even run a system where you have all the systemd stuff and all the system 5 init stuff installed in parallel, and everything will just work and will work in a natural way. Because we needed that for the from the Fedora upgrade from system 5 init to systemd. and they can just make use of that. So that's my personal opinion. Actually, nothing is stopping them. It's just that they think, it's okay running 2 different kernels, but it's not okay running 2 different or supporting 2 different instances. But anyway, we'll see how the discussions go. I mean, I'm not a Debian guy. I used to be a Debian guy. I even maintained a package once. But
another question, Mr. Watch, you might be aware of. They did a survey last year conducting what are the most popular distributions in the market these days. And surprisingly or not, the number 1 was Ubuntu, number 2 was OpenSUSE, number 3 was Fedora, and which is kind of interesting. Number 4 was occupied by Other, the distribution called Other. Now, most people who are actually answering this question for the selection of Other, they were able to select, they were able to actually enter what does it mean, Other. Now, yeah, this is my private thingy. The vast majority of those people actually mentioned Arch Linux. And I know that Arch Linux actually uses systemd already. I mean, it's not in the default install, okay? Because they normally follow the Gentoo-like RC system5 init script, but their integration with the systemd is quite good. Did you have to work with people from Arch Linux society or community in a way?
So there are basically 2 people from the Arch Linux camp who are very active in systemd.
Okay.
And they so Arch Linux apparently they don't have the guts to go systemd all full time. So they try to go like halfway. They want to support both, but they took a couple of systemd features and actually supporting that on non-systemd systems as well. For example, we have something called temp files, which is really useful to regenerate temporary files. That's what the name suggests, I guess, and /run and reboot, so that we have something reliable. And they decided, hey, that's a really good idea. We totally need that, and they added that to their normal distribution, even without this.
So you were approached by Arch Linux people while integrating
So no, they basically wrote that all in shell on their own. I don't think I wouldn't have done that. They should have just taken the binary out of
So they have
systemd.
just taken it, adapted, and used it.
Yes.
Okay.
So yeah, it's like you have so basically Fedora OpenSUSE went for it and made it the default. Debian has a huge fight. Ubuntu decided, I mean, I figured this discussion is very well known here, decided not to adopt it and is very loud about it. I think it's a huge mistake, but anyway. Gentoo has it in there, but I don't know, it's apparently currently run by people who think that system5 init is the best way to go. But I mean, they have something called OpenRC, exactly. So they have something called OpenRC, but which is basically the same thing as system5 init, and it's also not event-based, but linear-based. And I personally think, Jesus fuck, I mean, 20 years of computing happened, wake up. But I don't know, there's a couple of forks of... yeah, sure, if you only have one hard disk, but if you have anything that is more complex than just one hard disk you root from, then it's either extremely slow or it doesn't even work. So anyway, but a couple of forks. Like I don't know what there's one relatively nice one, and they because I mean Gentoo used to be something that always was at the spearhead of the development. It kind of changed. It's now, I guess, very much at the end of development, worse than Debian, I guess. That's my personal opinion, of course. I'm pretty sure that probably Gentoo people can say, "Oh, it's not like that." But anyway, they have this other fork which went for systemd. I don't know. But anyways, systemd isn't the distribution. So yeah, I probably shouldn't talk too much about the other distributions. After all, I'm not.
Anyone in the community who disagrees with you,
Yes, it is. No, everybody agrees with me.
And decided to create a fork, like systemd LG or something like that.
So the question was if there was anybody disagreeing with the decisions we made in systemd upstream and already forked it, and the answer is not that I was aware of. I mean, I know like systemd is something where we try to cover embedded to desktop to server all in the same way as this is done for the kernel. And we know. So what we know is that a couple of companies have built it into appliances, and they tend to patch this stuff and not tell us about that. So you could consider that a fork, but it's not because we didn't do what they wanted. It's because they do the walled garden development and just don't tell us.
So that doesn't mean that Lennart Poettering is the the most important person in the system development, or are you sharing development with other people?
So basically, we are a team of 4 people or let's say 3.5 people who regularly commit to
Good, 3.5.
to system D.
You have some legit in the team? You said 3.5.
No, the half guy is full time working on that. But it's basically it's there's 3. Most of the work is me, it's Kai Sievers and Michael Schmidt. All of 3 nowadays work for Red Hat. It wasn't always that way. It used to be something which was shared between Susan and Red Hat. And we have a larger group of committers. I think there are at least 5 other people who can commit, and they always commit fixes when I want. And then we got a huge number of people who send patches. We have a couple of companies supporting it. Who will do developments. If any of you have needs a company that does system development, that's actually, I linked that on the website of system. They're actually doing good work. So you all also want to do system development?
Yeah, I do.
That's probably what it means. Anyway, so you can get support from all areas, and the thing is like that. What we really want to make sure is that system D does not stay something that's our private property where only we can have control about, but it's something that is a healthy community project where a couple of people have access can commit to, and that belongs to everybody. This is very different actually from Upstart. It's one of the reasons why I think that Upstart has a huge problem, because in Upstart it's a property in a way from Canonical, and they exercise copyright assignment on it. That basically means they don't accept patches from you. They only accept patches from you when you sign a waiver and basically grant them the ownership of that. I personally find that that's a dickish move, and secondly, it's like giving the finger to all the developers who want to send in patches, because they say, nah, I'm not interested in your patch. Please sign this and give me all what you belong. The irony of it is even that no, like if you work for a company and you want to sign this stuff, usually your legal department will say, you're completely nuts, you will never sign that, because it has all this kind of patent language in it, which basically says, yeah, if they accept your patch, then you basically also grant all the patents that your company has. So it's completely unrealistic. Nobody in the same mind would ever send in a patch, because it kind of, I mean, all these companies, they all have these patents, but they probably should comment on the patent situation anyway. But anyway, so I think Upstart is drowned in a way by this copyright assignment policy, because they don't get as many patches as we get. They only have a single commission basically. Yeah, we want to be the author of that open. We take everybody's patches. We are totally happy with. We want to have. Yeah, we are friendly guys.
Okay. Another question. You are dealing with the kernel itself very closely, because you're the father of PID1.
I am the only one.
You are PID1. So my question is, if you're trying to were you actually approached by any of the old dogs of the open source community? You know, I mean, people who are influential, like Linus Torvalds, or maybe Andrew Morton, maybe I don't know, Marcello Vicetti, any guys like that. Were they looking at your project saying, hey, it looks promising, it's not our part, it's user-run thingy, but it's very close to kernel, we would like you to go that or other way. Were you actually approached by those people?
So we can only speculate what all these people think. I personally, so I don't know, there's no official statement from any of those. We do get feedback from the kernel community, from the broader kernel community.
You mean
Sometimes.
AKML itself?
Yeah, I mean sometimes very negative one, because there's one issue. I talked about C groups before, and C groups is a technology that is relatively new in Linux, and it is a very often misunderstood technology, because it's actually two things. First of all, it's what I was talking about earlier, a way to group processes and attach a label to it. The second part of it is that you can actually apply resource limits to these groups you created. So you can say, yeah, all processes of Apache, I give the name Apache. This is the left part. And then the other part is, okay, now I say it can only get this much memory. It gets, from the disk, it only gets this much I/O. It gets this much CPU time. It can only work on CPUs 25 and 26, and similar kinds of resource limits. Now, the first part is something that should be absolutely uncontroversial because it doesn't influence very much the performance of the kernel, because it's just attaching a label to process. That's one of the most trivial things you can do. The other part, the resource controller stuff, that is actually very different. Because if you want to control the CPU usage, you have to influence the scheduler, the CPU scheduler of the operating system, which is like the core of the operating system. If you want to limit the memory, you influence the memory manager. If you want to limit the I/O that can be generated on disk, you influence the elevator. And these groups make all these problems a lot more complex. So that's why the maintainers of these individual subsystems, or many of them, actually hate C groups very much. But they actually just hate the right part that I was saying. They shouldn't have a problem with the left part, because the left part doesn't do anything, it just puts labels on things. So the problem is that these two topics are always munched up. Nobody can distinguish that, including a lot of the kernel developers. So yeah, so basically this is the big thing that some of the kernel people hate. They say, oh my god, this stuff was my scheduler. I don't understand my own scheduler anymore. You guys are evil. But actually, what systemd does is, it uses the left part. It doesn't give a fuck about the right part. It can expose that for you. You can have a control where you can say, yeah, I want to limit the memory. But if you don't do this, it doesn't care about the controllers. So the summary of this is, what systemd does not influence actually the kernel developers much. It requires the left part, it doesn't require the right part. There's a couple of other issues why the kernel people don't like that. For example, the real-time people, and CPU scheduler people, they have this thing that they...
Impatient people. Impatient people.
Well, no, but so they have this thing that they try to look at the performance of the Linux kernel, how it behaved over a lot of kernel versions. So they always create this graph where they have these experiments that they run on the Linux kernel and look how it behaves in regards to real-time stuff. And then they see how it gets worse, how you see regressions happen and latencies increase and stuff like that. Or they see how it gets better. Now, systemd requires these C group stuff. Since C groups are a relatively recent feature, this basically means systemd does not group in systems where C groups are not enabled, like the naming part of C groups. The other part can be turned off. And that basically breaks their statistics in the middle. Because they always want to compare these old kernels with new kernels, but if they run a new distribution that has systemd on it, they can't do that anymore. So that's a valid reason. But I don't think it's a valid reason for a distribution or anybody else, but the kernel developers, to adopt it or not. And I mean, you could even say that if they do these tests, they probably shouldn't run anything at all. They should just invoke directly from the kernel that test process what they want to test, basically, because otherwise you always get corrupted by stuff that runs in the background and stuff like that. So anyway, so these are basically the reasons why some kernel people are very loud and hate it. Again, systemd does not actually require any of the bits that are really controversial. You can totally turn that off in kernel and not make use of them. And the other stuff that the kernel people have do not matter for anybody but these specific kernel people. So, yeah. Okay. Everybody sit down. Shut up. Hi. Ooh, sit down. Shut up. Okay, let's go on. So, yeah, I think the last slide I was showing was the one about redefining the project, and we made systemd basically went away from this idea that it should just be an init system and make it more the building block of the core OS. So, as part of the process of getting systems into the distributions, you of course need to make it interesting for the people. And a good way to reach that is if you actually care about the specific uses that the specific areas of Linux have, or requirements that they have. And so I call this winning the fiefdoms, like the personal private areas that people hack on. So for example, for the security people, we added a couple of gimmicks to make systemd really interesting to them. So one of that was basically that we integrated. So you want to hear how I drink?
Yes, I want to hear it. That's good.
So for the security people, we added a couple of features. Like one of them is We added SLinux support right into P81, something which wasn't really viable in System 5 init, which basically means we can now support init.rd and init.rd-less boots with SLinux and everything's labeled properly and all these kind of things. AppArmor, I mean, I'm not personally a security hacker, so I don't give a fuck. But I'm happy to merge these patches if that makes sense. For example, the SLinux stuff originally, I reworked it a couple of times because I didn't like it that much in one way and another, because it was a little bit slower than I wanted it to be. But ultimately, the original patch came from the SLinux people. And I would expect the same thing from AppArmor. So if people care about AppArmor, no. The thing is, like, I mean, there's no need because right now AppArmor is more or less something that is only used and actually maintained by Ubuntu. Like the two AppArmor people nowadays work for Ubuntu. And since they, or 2.1 or something, and since they don't, and since Ubuntu doesn't adopt systemd, ultimately, yeah, there was no need to get this merged. But anyway, if somebody sends me a patch of AppArmor, I think it should be handled the same way as we load the SLinux policy, which we should load the AppArmor policy very early at boot. So I don't have any fundamental problem with AppArmor. I mean, I personally think that SLinux is a better solution because the well-known things that you probably want to add the access control to the objects instead of the way you access the object. But that's more a philosophical question for security people, and I don't give a fuck. But anyway, so yeah, it's completely open now. The same way as we have support for SLinux, we also have support for IMA, which is a framework probably going to become more relevant. It's something that you can detect changes in binaries and does hashes and like checksums of binaries, and so that people cannot break in and corrupt your stuff and you won't notice. And this also needs a policy which we also can load from P81 if this is enabled. And there's a couple of other things that make it really interesting for security people. For example, we have this nice feature. For our service, you have this boolean which you can toggle, and if you put it to yes, it's called private TMP. The service gets started, but gets a private instance of /TMP. Why is it useful? /TMP always used to be the primary, or one of the main security holes in software. Because it's a shared namespace, anybody can create a file in /TMP. And you could use all kinds of mistakes that people made. Like, for example, the most basic mistake is just pick a fixed name in /TMP. Because everybody else can also pick the same fixed name that basically can DOS you, because somebody else already did create the file that you wanted to create. So it used to be like all the time. Like if you look at the security logs, where all this stuff announced, you will see it. It's basically in every 10 or so bug reports, you will at least find one that's about /TMP. So this private TMP thing, basically, it will give every service that is started, or individual service that is started, gets a private instance of /TMP. And whatever it writes in there is not shared with anybody else, and then all these problems go away. And there's another feature like that, for example, called private network. Private network basically means that if you set the boolean to 1 for a specific service, it is completely disconnected from the network. It gets its own private loopback device, but doesn't get access to any of the actual network devices. So you completely truncate network access for the service. And that makes a lot of sense for many services. For example, I don't know, policy kit just permission checks. The DDoS just routes messages. It doesn't need network access. And if it should ever get network access, then it would be probably a big attack surface. So yeah, we added this boolean to them, private network, which is set to 1, super easy to use, and you can be sure nobody gets into that. So yeah, so to get this to be effective for everybody, we added this feature. Then results management. As mentioned, we already use C groups, so a couple of how you can make use of the controlling part of C groups, which is basically for each service you can specify a really high-level function, for example, memory limit, and then you can specify memory limit 1 gig, and then you can specify that for Apache, and you can be sure Apache can never use more than that. Or you can it's a couple of similar high-level functions to say CPU shares, and you can say, yeah, this daemon gets this much CPU shares, and then this is in total. That's a bit different from the classic resource limits that we all know from Unix, because those classic resource limits mostly apply to processes, and some of them to users, but mostly to processes. And all these stuff that we can do with C groups basically apply to all the individual services. So regardless how many children Apache creates, how many CGI scripts it creates, in total you can limit the memory, in total you can limit the CPU share. So we made this attractive to the people who care about resource management. Resource management is absolutely important on servers, and in embedded as well. Because on the desktop, you have a lot of CPU and run very little stuff. Most of the time you just write a word processor, which means the CPU is entirely idle most of the time. This is different for embedded. On embedded, you usually run quite a bit of stuff, and the available CPU power is very limited. And on servers, the available CPU power is big, and memory and everything is big, but you also tend to run a shitload of stuff. Now even more than previously, because nowadays you have clouds and shit like that, and virtual servers and all these kind of things. So resource management is absolutely important for both these things. It's actually, I mean, I always find it actually interesting how these features that we add to systemd that we think are useful, for example, for the server, end up being incredibly useful embedded as well. Or something that is useful for the desktop ends up being useful for embedded. Or something we add for embedded ends up being useful for the server. It's surprisingly often that happens actually that these three big areas actually share the same needs way more than people expect. I mean, I want to land it again, like in systemd we try to cover all three bases. The same way as the Linux kernel is useful for all three. So desktop, embedded, and we want to do that for systemd as well. And I mean, I can name a couple of more examples. Like for example, for high availability service, you need the ability to support hardware watchdogs. Hardware watchdogs is a little bit of hardware that is built into all modern servers basically. And even actually my desktop has that built in too. And if you have the input board, you have the watchdog device as well. The watchdog device is a very simple thing. Basically, software has to send a message to this hardware device every so and so often. You can configure it every minute or so. And if the software doesn't do that, the machine will reboot after a certain time. This is useful for servers, because high availability service basically means, yeah, you need to guarantee that the server is reachable all the time. And because servers are made by humans, and humans suck, they will eventually freeze and not work anymore. So we added functionality to support these watchdogs. So that basically means, first of all, services can be individually watchdoged, so that the services have to send systemd itself notification minutes that we exist, and systemd will then ping the hardware watchdog, so that the hardware will watch systemd. So you have this chain of having everything watchdog, and you can be sure basically that if something goes wrong, you either restart the service, and if it doesn't work, you restart the machine. It's always kind of robust. So the high availability server people needed that, and it's built in all to the servers. But the other people need that the same way. Like Linux is nowadays built into cars. And in a car, it's kind of essential that, for fuck's sake, the board computer should always work. Yeah, they said, we won't take anything that doesn't have a watchdog. Oh my god, we added this for the server people to systemd. And they were so happy because that's exactly what they needed. They have exactly the same use case. On the desktop, of course, nobody gives a fuck about watchdog. Anyway, so just a little bit of an X-course, how it's, it has a couple of more examples like that, where these three things, where people always imply they have completely different needs and requirements, actually end up having very similar requirements, and where it's really useful to cover them all. So yeah, we try to win over a couple of other people like containers. Like systemd has basically you can start up a system in a container, in a Linux container, like LXC or nspawn and a couple of other implementations, and it will just boot up plainly. And it will do the right thing. So it basically will, I mean, if you boot up systemd on a normal system, it will do all kinds of hardware management. Like it will start UDEV, it will set up the console and stuff like that. In a container, you don't want that, because in the container, you don't have a hardware access. It's a virtualized system. So you don't want to have the console initialized. You want to start UDEV and these kind of things. So we carefully made sure that systemd actually spawns in a container. It does the right thing. It doesn't start all this stuff, but only the stuff that's actually really necessary. So we try to win those people over. Then with HA, like high availability, I already mentioned, like the watchdog stuff. That's what they want, so we added it. And there's a couple of other things that we still need to add. And we really try to focus on everything, like where this matters, so that we make them happy. We're trying to make something that also might make other people happy. For example, on the other end, on the embedded. And yeah, we added a couple of things for storage that makes things happy. So we really worked on making the system be attractive for the individual fiefdoms of Linux and development, so that they say, yeah, with systemd honest it works. With system flat it doesn't. Systemd is awesome. We want that.
Okay, Lennart, you mentioned some car manufacturers. Do you have any feedback from car manufacturers about systemd?
Yes. So I was actually 2 weeks ago. I was in Paris at a conference by Genevieve. Genevieve is a consortium of car manufacturers, like it's BMW and a couple of French ones, like Peugeot or something like that, and a couple of American ones, and a couple of Japanese ones, and even Chinese ones.
Chinese manufacturers of cars.
Yeah,
That's a big word. That's a big word.
Anyway, they built they built Linux into cars. It's not for the actual driving. Like everything that's actually really life dependent is not run by Linux, because I mean it needs to drive the car. But everything else, like it really depends on the car. What else? They want to integrate into one computer basically that they have in there with some ARM embedded chip, usually relatively high powered, but which will do the multimedia system. It will do the seat arrangement. So you stick in your key and your seat goes in the right position how you previously used it. It will do the lighting system. It will do the distance measurement stuff, that beep 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 stuff thing, and all this kind of stuff. They want to use Linux for that. And then they wrote a specification, basically what these what systems. It's in vehicle infotainment. Yeah, something that they wrote into that is actually that all Genevieve IDI systems need to have systemd on them. Because, yeah, they wanted all these features. Like, for example, the watchdog stuff is something they totally love. They want that in the car. And a couple of other stuff, like the general service management, is absolutely what they need. And yeah, and so they said, yeah, absolutely, this is exactly what we need. They had 2 issues or something that they still wanted, and they love it. So yeah, it's really interesting actually to see that, because systemd is nowadays used in cars. I mean, you can't buy them yet, but it's what's developed by BMW and all these kind of things. You can very soon buy a BMW that runs systemd. But on the other hand, it's also used in toys already. Like a big Danish toy manufacturer.
Lego?
Lego? Is building that into toys. So yeah, we made our stuff attractive for embedded people. We actually do care about them, and we actually see the big picture there, that something that's interesting for embedded is also interesting for server sometimes, and also interesting for desktop sometimes.
Were you actually approached by the army?
I mean,
The US Army or any other army that has...
I mean, usually they're kind of secretive about what they do. We know that they use Linux in many ways, and I would expect they also use systemd already, but I have no such information. I'm not American, so they won't talk to me anyway, and they're secretive. So. Yeah, but I mean, they use Linux all the time for the weapons, and I'm pretty sure they will end up using systemd if they're not already doing it. Yeah. Next thing. Of course, you immediately get to this problem that if you as I mentioned before, we stuck a reader head and a couple of other things in the systemd, and we try to make all these fiefdoms happy, like the people who care about security, the people who care about those stuff and all these things. Then you immediately create the problem. Okay, where does it end? If we put all this into systemd, yeah, does systemd become this huge thing that does everything and tries to make everybody happy? And it's a good question. Like, there's no clear answer to that. Does it become that, or doesn't become that? We think it hasn't become it yet, and we always think about it like, where do we put the limit? And we look at the examples that exist, like the Linux kernel, for example, has the same problem. It tries to be something for everybody. It does resource management, does security and things like that. But there are certainly people who say Linux is bloated and stuff like that. But in general, I think it's kind of accepted that it's useful and embedded in on servers the same way. And they managed to avoid this discussion pretty much. So we think we can do the same thing with systemd. We will grow a little bit in the modules we have, but these modules like most of them will stay completely optional. And as long as you disable them, this doesn't have an effect. So yeah, but the question still belongs: where does a system start? Where does a system end? What else are we going to pull in it? I'm pretty sure we will pull a couple of more components that we think are really, really basic for operating systems. But the thing is, like, our goal with system these days is provide the tightly knit set of really basic operating system components where we believe that at least 75% of all users will need that. And we came to the conclusion, yeah, Reader Head is something you want. Because Reader Head is actually something that's really useful on desktop. It's really useful on embedded, because you need, like for the car manufacturers, for example, they need when the keys turn around, they can only wait for 4 seconds at maximum until the car's powered up. Otherwise, people will go nervous in the car. So this is a problem set that, yeah, we say this is embedded, this is desktop. We think together we probably cover 75%. It's completely irrelevant on the server. Quick boot ups on the server don't matter. I mean, they do matter in some way. People don't always see that they actually do matter, because servers can be large these days. Like, for example, SGI built servers with a couple of thousand CPUs and with a couple of 10,000 hard disks. And if you come into these ranges and you do this bullshit that I was previously talking about, like for example what Gentoo does, when they boot up, you try to wait until everything got enumerated and stuff like that. This doesn't work if you have to wait for 10,000 disks. You can completely forget that. So yeah, fast booting, that's just a slide, actually does matter for the server as well. It's not a crashing issue, and it has a different characteristic, but it does matter. But anyway, so yeah, basically the question for us is what does belong to system, what doesn't? And yeah, we try to decide on the individual thing, and then if there's a very good implementation, we'll stick it in, otherwise we won't. But for most of the stuff, of course, we'll stay as optional. So we make this offer. Hi, we offer these tightly integrated stuff, but the distributions who want to adopt systemd have the ability to say, yeah, we want to use, I don't know, the retemple implementation of somebody else instead of the one of systemd. And we say, yeah, whatever, do it. We just make an offer that ours might actually be more interesting, but you don't have to. So, but it's really the question. It's a really good question. Like, where is the limit of systemd? I don't think we have to reach it yet. The same way as the kernel keeps growing and growing and growing. We already have said no to a couple of things where people have said they want to see the system. Yeah, the one I'm thinking of right now is, for example, there's this journal thing that we talking about logging, and people have requested that we would implement the compatibility protocol for systemd that outputs things in the classic RFC protocol. We have an input thing because we need that for compatibility reasons, because all the applications generate that stuff. But we thought no, because this is not what we think that everybody needs. That's what enterprise people need to connect systemd to something else, and it can perfectly live outside. So, but it's a tough decision sometimes. I mean, it's not clearly that it says no, this can't be in there, but yeah, this is something where we said no. There are a couple of other things where we said no. It's a different question, a difficult question. It's always easier to say yes to something when it is entirely modular. It is always easier to say yes to something where we have a personal interest in, because then we know that we can maintain it and we don't rely on other people maintaining it. But yeah, sometimes we say no, sometimes we say yes. So, next one. So, as mentioned, we discussed it before, so I don't have to talk about it very much. Fedora OpenSUSE as default, and then that's all the rest. I also talked about this a bit. We always get this complaint, systemd is bloated. I don't think it is. I think actually it's the opposite. So the reason why people say it's loaded is because it does so many things. Because it has a read and head implementation, it does logging now, these kind of things. But honestly, I'm pretty sure I will win every bet that if you put together a system that does even remotely equally as much as systemd does, you will get 10 times the footprint that systemd does it in. Simply because we get rid of the duplication. We get rid of a lot of stuff that we collected over the years. We don't do all the abstraction stuff that everybody else does. And so, in the end, yes, systemd does a lot more than traditionally in systems did. But it doesn't mean that it's bloated, because if you build a system based on systemd, you need like, I don't know, 15 minimal components, and you're done. With a classical system, you need at least 40 or something components before you have put together your system that actually boots up. Like components, I mean like glibc, the kernel, blah, 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 blah. Because in the classic system, you need a logger, you need cron, you need add, and these kind of things. And you don't really need these anymore if you use systemd. You can use them, of course, if you want to, and want the compatibility. Yeah, so my claim is, if you build your system on systemd, it's the opposite of bloat. It will effectively get smaller and we'll get more out of it. So yeah, that's my usual reply to that. And yeah, I actually believe that. I mean, there's this. I read a couple of weeks ago an interesting scientific paper about the psychology of bundling stuff. And there's this fact that people assume that if things are bundled, the things that are bundled are worse than if they would get it independently. So an example for that is, for example, you go to your technology shop and you want to buy a TV, and they offer the TV that is a TV, and they offer you a DVD player. And they also offer you the TV where the DVD player is built in. Most people implicitly assume, yeah, if I buy it separate, I get too high quality product, I get the bundled thing, whereas this built in probably sucks. So this is a psychology thing. But it's psychology, and it's not true. It doesn't have to be like that. Like actually, if the DVD player is built into the TV, it could be much nicer integrated, much nicer to set up, because you don't have to set up all the wiring and shit like that. You don't. You need less space, less energy, and all kind of shit. When it's done properly, it can be much better than a separate solution. So, and that's exactly the same here. It might be this psychological trait that people say, oh yeah, it's bloated, it's huge, it does everything. And it's anti-Unix, because in Unix you have 10 components, we did individual things very good. And this one does everything. But it doesn't mean that we are not doing it good. We try to do it as good as we can and tightly integrate it. And the other thing, like if people complain like that, yeah, do one thing and do it good, is, yeah, we have a couple of components, and each of those components do one thing and do it very good. Systemd is not, and that is something that miscomprehension that some people fall into, is that systemd was one huge process that would do anything. That's actually not the case. Systemd is a set of services, and in that regard, it's very much in Unix. So yeah, our answer to bloat is less duplication and more modularity. That's why it's not bloat. The other big criticism we always hear is that systemd was not Unix-ish. And honestly, I think it's completely another bullshit. The thing is, like, different people understand different things under what is Unix. For example, one really often heard definition of what is Unix is this thing like, Unix is everything is a file. I personally think it's complete bullshit saying that, because my printer is not a file. My printer is a fucking printer. It's not a file. I cannot store anything on the printer. It doesn't make any sense. So, I think when people claim that everything's a file is a good metaphor, I mean, I personally think it's a wrong abstraction. Pretending that everything is a file and the printer is a file, it's just a wrong abstraction. It's just not a file. But I think what they actually want to say is that everything exists in the same namespace, which we call the file system. Because that's what happens, because a printer is probably called def-lt0 or something like that. So, and that is one of the good core ideas of Unix, that everything that you have on the operating system appears in the file system. Now, if people claim that systemd wasn't Unix, I can answer to them, fuck yeah, it's really Unix. We are much more Unix than System 5 was actually, because we actually expose services in the file system, both as files, you can just see them as foo.servers, and during runtime, they are available as C groups, and C groups are exposed in the kernel to user space as a file system. And you can go to it, you can CD into it, you can cat files, you can see what servers are running, what the processes are, and so on. So if people tell us everything is a file is Unix, and on systemd it's not Unix, I can tell Unix is than Unix ever was. We expose everything in the file. And there are a couple of other things like that. If people say we're not Unix, I can give you a couple of things where we're totally Unix and more Unix than was before. Like, for example, another thing that I actually announced like a couple of weeks ago was something called multi-seat. Everything's okay?
We're running out of tapes.
Oh, are we? That's good. So now I can talk all the real dirty shit. So, yeah, the other thing that I was talking about is something that I announced the work that we did a couple of weeks ago was multi-seat. Multi-seat.
That's the feature you're actually very happy about with the Fedora 17, aren't you?
Right. Yes.
Those of you who actually follow Lennart on G+, you will see that he's very happy. I think you call this the best uncalled, unknown feature of Fedora 17.
Yes, I call it the most awesome but least known Fedora feature. Because we didn't really have a feature page about it, so it never showed up on the things because it's kind of misleadingly named in Fedora. But basically, what multi-seat is basically that you have a single computer and multiple people can use it at the same time. There are basically multiple seats, multiple screens, multiple keyboards, multiple mice, and they can use the machines all at the same time. And it appears to them as if they all had an individual machine. This is totally awesome because it saves power, saves space, saves administration costs, and so on and so on and so on. Now, the idea of multi-seat is absolutely not new. It is absolutely Unix. Because in Unix, you had these terminals. I mean, nowadays, the fewest people use terminals. I mean, some people still do. Terminals are basically just seats. They are screens with keyboards and probably not a mouse, but some externals actually do have mice. But yeah, they kind of went out of fashion these days. But they're still built into the kernel in very, very weird ways. Even if you have not a real terminal device on your machine, you still have virtualized terminals. Like you have the virtual console and you have pseudo-TTYs. Most people don't even know about that. They actually still have this terminal technology built into everything that Linux does. But anyway, it kind of went out of fashion because it didn't go with the times. Because classic terminals are text-based. And nowadays we want everything graphical and with effects and stuff like that. And because nowadays a workplace usually is not just a keyboard and a screen, but it's also a mouse. It's a sound card usually. It's a webcam. Can be anything else. So what we did with the multi-seat stuff is we just took this old Unix idea and took it to the 21st century. And we said, yeah, we want something that is hot pluggy, that can support all kinds of devices, and but brings back the good old times so that we can actually use one machine with multiple people to save money. So yeah, if people say we're on Unix, fuck, we're totally Unix. We bring all the good stuff back that Unix always was. I mean, Unix is a lot of things. Unix is a lot of bullshit. Like there are a couple of APIs that were collected over time that are just moronic. I don't know. Like if I say something force, which is I don't know how many people of you know that it's a
Oracle thing.
the what?
Oracle thing.
No, it's just something how
Today
process.
it's mostly used by Oracle people.
Yeah, it's also used by X actually. It's basically it's a technology that is used to synchronize multiple processes which want to access the same data. And it's a really horrible API. Nobody should ever have invented it. And they're much nicer APIs these days. So Unix is a shitload of stuff, and it's different things to different people. I personally say, yeah, Unix is a great inspiration. It is in a way a little bit like democracy. I mean, what they say about democracy is that democracy is really fucked up, but it's still the best thing we have. And I think that's very true about Unix as well. It's totally fucked up, but it's the best thing we have. So, and based on this idea, we say, yeah, Unix can be a great inspiration. And there are a couple of features that got lost in history, like for example, the multi-seat support, which was called terminals that were behind. And we just want to say, yeah, that's good. We want to bring that back. We can do it much better now, and we want to do that. So anyway, if anybody says system is on Unix, I can give you a million reasons why it's totally Unix. And we're working on making it even more interesting. So, so what is un-Unix-ish about it? Of course, there's a couple of things like cron and apps and stuff like that. And System 5 init scripts. We kind of obsolete those stuff. But we continue to support them. Like Systemd can read System 5 init scripts just fine. Not all of them, like some people use really weird shit in init scripts and they're not supported. But most of them, like 99% are supported. And at the cron, you can continue to run the system if you want, but you can also use the system internal stuff. So, yeah, it really depends what people see in Unix. But I would claim, we are so totally Unix. And we're adding features all the time.
Okay. How about we go to the panel discussion?
You want to go to the panel discussion?
That's,
I think.
how far are you from the end?
Not at all. I have so many slides. A gazillion actually. You can probably see that as this. See, I got 90 slides or something. But I never had the plan to ever cover them. It's just fallback in case you guys never say what question in the panel discussion that will follow it. So I'm really happy they're doing this panel discussion.
We can go on to the panel discussion. So, guys, panowie, jeżeli macie pytania, po angielsku śmiało, bezpośrednio do Lennarta. Jeśli po polsku, spróbujemy tłumaczyć, więc nie ma znaczenia, czy macie trudne pytania, czy łatwe pytania, spróbujemy. Więc pierwsze pytanie, co jest w sali.
I had a question. I think that person you answered already that, but if you could a little bit more elaborate about usage of system D in system on chips things or some small, small factor.
Yeah, so I guess the question is mostly about how useful is systemd and what's the benefit of using systemd in embedded systems, like the smaller kinds, the ones that people not use, like a desktop. So, as I mentioned, systemd is designed, we don't care either. What we care about is basically the bigger embedded devices, like the range of a mobile phone, the range of a TV, the range of a car, where you actually have a little bit of, you have to run more than just a few services. Actually already where you have more to run than just one. Where the available resources are not entirely true. If you use systemd, you have the option, you can tailor basically systemd to whatever you want. And systemd is designed to be as maintenance-free as possible. What does it mean? Basically, with systemd you want to design a system that you can put on a machine, start the machine, put it somewhere in the corner. 2 years later, you can come back and it will still run and do the right thing. Linux currently, the way it traditionally was, not so sure you can do that. Example. For example, traditional syslog. Every now and then, so basically a syslog is very, very simple. Whenever an application wants to log a message, this message is just written to the end of a log file on disk. And it grows and grows and grows. And then, depending on a cron job, every now and then these files are rotated. So the old stuff is deleted, and the stuff is renamed and so on. Now this, on the first look, it looks like a good system that could work for 2 years. But actually it's a little bit dangerous. Because what happens if in a very short time frame that is shorter than the rotation interval, some application ends up writing a shitload of data. And that happens. Because if applications crash, if the application misbehave, they end up generating often quite a shitload of messages. So what happens if in this really short time frame, a ton of messages are generated? The syslog daemon will usually just write that to disk. But it will still wait for the hourly rotation or something like that, or even the daily rotation. And at that point, the hard disk might actually be full. What does systemd do against that? For us, rotation is not something you add for an external. Rotation is something that is done in the journal, and I didn't really talk about the journal. The journal is basically this thing how we reinvented syslog in a way, and pulled it because we believe that absolutely integral part of service management. So we pulled that into systemd and called it the journal. If you want to know about that more, there's a big article about that. But anyway, the journal, the way it does rotation is synchronously. So whenever it wants to write something to disk, it checks if the disk is full. If it is full or if the limits are reached for the rotation, it will do that immediately before writing it. And thus it can guarantee you, whatever happens, even if an application completely runs amok and it generates a ton of data in a very short term, rotation will happen at the right time and nothing goes wrong.
It's a very lengthy answer to a very simple question.
So yeah, sure. It's kind of it is one example how we design this stuff. We want to have something that just works whatever happens. And current Linux is not designed that way. So, and then there are a couple of other things like that, like for example, like if the service crashes, you won't have to restart it. With System 5 minute, you can't do that. But you totally want that on embedded devices.
But
So,
also, I have a question. By the way, you were talking about embedded stuff. Do you know how Android works? Or how does it compare to the system approach?
So that's a very good question. So in case you listen about that, the question was basically about how does all of this compare to Android and the Android boot. So yes, we looked a lot at the Android boot. It's quite interesting, but it's also very, very simple. So Android does a lot of compromise because they don't need to be general purpose OS. So basically, the early boot process is written in C. And it's just a program that's followed. That's not unlike actually the first bits that happen in systemd. For example, in systemd, stuff like /sys/proc/run, all these things are mounted in from T81, and because we know we need this anyway, and there's no point in exposing that as services, because it's so basic, it's every single of these operations is system call. So, and they have basically done the same thing. It's a lot more, let's say, focused on what they need, but it's very similar. And then they have Service Manager that is also not as interesting as we do. And then you get all the Java stuff and stuff like that. So I think it's a good design what they have there, but it's a very specific design for them. It's very Java bound for them. I think it's probably what you want for a phone, I don't know. But systemd probably is very interesting for a phone as well, and has the benefit that it's more generic. Because we write everything in C, probably even faster, and because we have all these features, it might actually be more interesting as well. Like, as far as I know, I mean, they use C groups and these kinds of things for a couple of things, but I'm pretty sure they haven't exposed them as nicely as we do. So, I don't know, I think Android is good. I mean, Android is not a general purpose OS, but I think Android has a lot of, it's another good source of inspiration, actually. It doesn't mean that we need to follow whatever they do, but in that regard, it's not too novel, not too radical, but in other ways, it's really interesting as inspiration. I hope this kind of answers the question.
Okay, another one from me, correctly. Between Flash, Adobe Macromedia / Adobe Flash 9 and 10, one of the biggest differences, one of the biggest changes was to support not only ALSA, but also Pulse Audio. Now, my question is, the reasoning for that is obvious. Everybody understands that this is the way to go. The question is, were you actually approved by Adobe / Macromedia people when you were developing Pulse Audio?
So I actually met the guy who ported Flash to Lennart, and this is this is not on video, so I'm not going to say
We're gonna cut
anything.
it out. I told you, we're gonna cut it out. Whatever you want, we're gonna cut it out. It's just for these people.
So anyway, I met this guy. So let's say he had very creative ideas about how audio works, and I was a little bit surprised by that because yeah. I did talk to them. I wasn't too impressed, but basically, so what I did basically back then is to get the compatibility with Pulse Audio. They have a backend, a pluggable backend thing, and I wrote the backend for that. So actually, the old Flash version worked too. And then they did their own stuff. They keep on breaking this all the time. I don't know.
One of the biggest
It's like
problems, one of the biggest problems with audio.
so that I did talk to them, but there was no explicit communication about this. But anyway, yeah,
The
continue.
biggest problem with audio was always that the main vendors, like Macromedia or Adobe or anyone else, they were claiming that Linux software, Linux sound stack sucks.com. And they were claiming that there are a gazillion of methods to work with these
Yeah, absolutely.
OGSD, the ESD,
Yeah, they're absolutely right with that.
ALSA, this or that, Jack, or for instance,
They're
Jack.
absolutely right with that.
And how do you feel that Pulse Audio actually made the whole situation be settled? It's like
I don't think it's settled. I don't think it's settled.
Dog. We have Alpha Dog here. It's called
So-
Pulse Audio.
So, I mean, when we pushed in Pulse Audio into the stack, what we did basically there is there was ALSA and there were applications, and these were directly talking to each other. And then we had Pulse Audio, and we said, now we don't talk to each other anymore. We now push this in the middle, which is of course a big political issue. Blah blah blah. You probably know all the discussion. Now we were hated for that.
Yeah.
So,
Lennart.
so of course, if you do this, you have to have very good reasons for that, because I mentioned this irony before, that if you want to have standardize everybody on something, it's kind of crazy idea to create a new API, and then you have, instead you have 25 APIs, you suddenly have 26 APIs. So for standardizing something, it's a really bad idea to come up with a new API. But if you have other reasons to do that, then there might be good reasons to come up with a new one. I think the Macrometa people were right, and I maybe kind of, I mean, I don't think that they're right anymore, but yeah, Linux had this problem that there were so many different APIs, and there was no clear message on what is the one that people should use. And I must say, even nowadays, it's not always clear. I mean, it really depends on what you want to do. So basically, it's nowadays you have Alza, which is a supported API. You have Poettering, you have Jack, and you have GStreamer. Those are like the big four components that I think are part and should be supported by the various distributions as APIs. So basically, Alza you use if you want to write really low-level stuff for embedded. If you want to do, I don't know, specific experiments for physics and stuff like that. It's PCM. Poettering you use for everything that is basically that mobile phones for desktops, for everything where you have consumers working on this. Because it does all this fancy stuff for you, like surround management. It will do jack sampling, all the stuff that you need for the desktop and mobile and these kind of things. And then the third area is you have Jack, which is basically professional audio, which basically you create music. It's hard to use. It is shit with power management. It is enforces floating points, which means you always convert your samples basically before you write them out. But it is the best thing you can use if you do create audio. And then there's the fourth thing, which is GStreamer, which is basically if you want to play music or if you want to play a movie, it will schedule everything properly for you and decode it and these kind of things. So I think these four APIs are the API. Okay, that's actually the fifth one. The fifth one is something called Canberra that I actually wrote. That is the Canberra, like the capital of Australia, which is an API that generates, which is just for event sounds. It's actually kind of fancy. Like event sounds are basically these annoying things that happen if you log in and it says blah blah, and if you click a button it says click, and these kind of things. Most of the time they're annoying. They actually have uses, for example, for handicapped people, and they sometimes have uses even for non-handicapped people. Like for example, I find it really awesome that if I download a torrent, of course it's going to remove that.
It's a Ubuntu torrent.
Yes, if I download a Ubuntu torrent, I would never do that. if I download 17 torrents, that after it's finished, it does bing and tells me that it's finished. Because yeah, that's like a really nice feature where you actually need to make that sound. So anyway, and it has a couple of things that are actually really fancy for handicap. For example, it can position event sounds in space. So if you click on the button there, it will, like with stereo effect, it will say, it will make sure that the sound comes kind of from that direction. If you click it there, it comes from that direction. So anyway, this is what the event sound stuff does. So with these five APIs, basically we cover all the bases.
What about games? What would you say to game developers?
To what developers?
Games.
Games.
Yes.
That's actually a good question. I don't have the answer. It really depends. Probably you want to use something like OpenAL or STL.
What
But
about the recent announcement that Steam is going Linux? And everybody's
honestly,
about
I'm not much of a games guy.
Steam's going Linux, and everyone knows that, and everyone knows that the Steam engine is
So-
also Linux ready.
So in general, I think it is wrong if you start a project that wants to output audio. I think it is wrong creating your own abstraction layer for different patterns. So use, for fuck's sake, one of the existing ones. And use one of the better ones. And the better ones are the five I just listed, or OpenAL or STL. But
And
don't.
if there's nothing better than this, create system D.
Well, yeah, and No, I think yeah, the summary of it all, I guess, is it got better. Like we don't have ESD, we don't have OSS anymore and these kind of things. We don't have ARTS anymore. We got rid of a shitload of legacy shit, but it's still kind of complex. Now the thing you could always say, oh god, the Linux people, the Linux audio people, they failed in big time because they still have 5 APIs. I don't think it's a big failure because if you actually look at core audio, like which is the benchmark, it's the Apple audio stack. It has this one name called core audio, but actually core audio is a set of different APIs that are not all written in the same style. They are not as different as ours are, but they are actually surprisingly mix and match. So they have a counterpart for GStreamer, they have a counterpart for the Canberra, they have a counterpart for Alsa, and for Poettering. And applications can also use all these different APIs. So in summary, yeah, it kind of sucks that we have 5 APIs, or maybe 7 APIs if you add SDL and OpenAL to that. But I mean, and on macOS you also have support SDL and stuff like that.
You also in sound, when you talk about games, you also have this weird shit that does 3D sound and all this. I don't know if it's really.
Yeah, but for that you probably want to use OpenAL and nothing else.
Yeah, but how does it go? Because the Pulse Audio releases just a PCF device. So yeah, I don't know exactly. But
So OpenAL has a Pulse Audio backend basically. So the thing is, the message I wanted to say is basically use, for fuck's sake, a modern API. And that could be SDL or could be OpenAL, because OpenAL, they already have these backends. But yeah, it's the same thing like, yeah, if you write a UI application, you have to choose a game. What? What's that supposed to mean? It means hi?
Hi.
Hi.
We got 5 minutes left of audio and tape.
Okay. But I guess you could even go on afterwards, I don't know.
Make it precious.
5 hours.
Okay, so we have a difference.
Make it precious, please.
So you want the really juicy stuff now? You bunch of sucks. What was I saying? Anyway, anyway, yeah, I think the summary of it all is, yeah, the situation got better. Much better, I would say. It might appear still complex because if you write an application and you don't know which API to use, I think that's a general problem that we have, is that we have a difficulty on Linux and telling people what API to use for what. That's probably one of the major hindering problems why people don't write applications for Linux, because A, they don't know which API, and B, every distribution supports a different set of APIs, and every desktop supports a different set of APIs. But I think, so basically I think we are pretty much as good as we can get in audio. Maybe we can get rid of 1 or 2 more APIs, but eventually it will never get better in that area, and the right approach to solve this problem thoroughly is probably more an issue of documentation. So basically, for example, what I would find really, really useful is having a centralized place where first of all, it's like a website or something where it guides the developers through, I want to play an event site, and then it would just say, yeah, go look Canva. And the other question is, I want to play video, go GStreamer and stuff like that. And then all the different APIs that we have are actually documented in the same style and same quality. Because right now, all these projects have completely different documentation styles and quality and all this kind of stuff, and it's really fucked up. So the summary to take of this, yeah, audio is nothing anybody makes money off. So that basically means I mean on the Linux audio stack, like there are 2-3 people working full-time. I used to work on the full-time, but now I got sucked into this other project you might have heard of. And the result is, it could be much better, but it's unlikely to make any big jumps anytime soon, because the people who work on it are busy with what they're doing.
A punchline.
A punchline, Pulse Audio is awesome.